Hi, and welcome back to IV Tutor. We are looking at binary trees in this video. And, a binary tree is simply, made up of nodes where each node has a left subtree and a right subtree. Well, can have a left and a right subtree, which means each node, which is referred to as the root node, can have a left and a right subtree, or a left and a right child. So, and it's most two. It cannot have more than two, which is where the word binary comes from. So, which means A can only have two children, B, two children, E doesn't have any children, but can have two children. So each node can have at most two and at least zero. So these here are just representing that there is nothing on the left subtree of D, and there's only G on the right of G, and there's nothing on the left of G, and there's nothing on the right of G. But this is what a tree looks like. So it's not very difficult to notice if you are given a binary tree. And whenever you're given a binary tree, some of the basic things you need to know is what is the level of a node. So the level of a node is the number of branches in the path from the root node, which means the level of A is 0, the level of C is 1. So you're just counting the branches, which means the level of D is 1, 2. So 2, 1, 0. That's the level of a binary node, of a node. And then the height of a tree. So I want you to notice that we speak of the level of a node and we speak of the height of a tree. So when we talk about the height, we don't talk about the height of a node, because a node doesn't have a height. We talk of the height of a tree. And the height of a tree is just the longest path to the last node, which means in this case, the height would be 1, 2, 3. So 3 is the height of this node. So the height of a binary tree is the number of nodes on the longest path from the root to the leaf. And the leaf nodes are the ones that are right at the end, which do not have children. So a node which doesn't have a left in the right subtree is referred to as a leaf node. Okay, that's it. And when we talk about trees, one of the most important things you should be able to do is to traverse a tree. Like, how do you go through every single node in a tree, right? And there are 3 ways you can traverse a tree. There is in order, pre-order, and post-order. And with in-order traversal, you start with the left node, then right, which means all traversals will always start from the left before going to the right. The question becomes, at what point do you visit the node? So if that can help you understand where the in, pre, and post is coming from, which means if I draw a tree here with A, B here, and C here, I'm saying you will never traverse C or visit C before you visit B, or you will never print B, you will never print C before you print B. So you will always go from left to right, but this is now being referred as the node. So we are saying here's the node, here's the left, here's the right. So in order means you're starting from the left, then you visit the node, then you go to the right. Pre-order before, it means you start with the node before you visit the left and then the right. So it's node, left, right. And then post after, which means you visit the node after going from the left, right, and then you can visit the node. So that's basically how you remember, which means if we print this node in order, we are simply say B, A, C. So in this case, in order traversal of that node would be B, then A, then C, which means before you visit the node, you have to go to, you just do it in order, left, node, right. That's in order, left, node, right. And then pre-order, you start with the node, then you go left, then you go right. So in other words, it's node, left, right. So in this case, we are saying you start with A, then you go to B, then you go to C, because you start with the node, then you visit the left, then you visit the right. So A, B, C. Post order means you start with the left, then right, and then node, which means in this case, it would be B, C, A, which means it's left, right, node. So that is what you need to really remember. In order traversal, left, node, right. Pre-order, node, left, right. Post order, left, right, then node. So post order ends with the node. After visiting left and right, then node. Pre-order, before you go to the left and right, you start with the node. So pre-order, it's node, then left, then right. And then in order, you just do it in order from left to right. So left, node, right. That's how you traverse a node, which means if we look at this tree here and we want to traverse this in order, right? You have to apply this method recursively or every time you visit a node. So we are going to start from the root node. You always start from the root node. And then you visit A, and then you say, I'm going to use red for in order here. When you visit A here, you're going to say, in order says, before you print A, you have to start with the left of A because it's left, not right, which means you have to go to B first. And when you get to B, you still have to apply in order, which says before you print B or before you visit B, you have to start with the left because it's left, not then right, which means you have to go to D. And before you visit D, the algorithm says you start with the left, but now there's nothing on the left. So you can say we are done with the left, which means we can actually now print our node D, right? And now we can go to the right of D where we find G. Now that we are done with the left of B, now we can print B because it's left node right, which means now we can go B. And now that we've printed our node B, we can now go to the right, which is E, and print E. Now that we are done with the left of A, we can now print our node A, and then go to the right where we find C. But before you print C, left first. There's nothing on the left, therefore left node. That means we can now show our C, and then we go to the right. But before we print F, left first, which means we go to H, then node, which is F, and then right, and there's nothing on the right, which means this is your in order traversal of your tree. So if we quickly redo this again, you can just look at your tree and go, I'm doing in order, so it's left, not right. So I'm gonna have to go to the left. It's in order, it's left, not right. Okay, in order, there's nothing there, so it's node, right, node, right, node, right, then left, then node, then right. So this would be D, G, B, E, A, C, H, F. That's how you do in order. All right. Now let's do pre-order. Pre-order says you must start with the node before you visit the left and the right. So I'm again going to start from the root of the tree. I'm at A. What am I doing? Pre-order. Pre-order says start with the node, which means I start with A. What do I do after that? You go to the right. So I go to B. When I get to B, I'm still doing pre-order, which means start with the node, which means I start with B, and I go to the right, I get to D. When I get to D, I'm doing pre-order, which means I start with the node, which means I start with D, then I go to the left. There's nothing on the left, which means now I can go to the right, and I find G. Done. Then I'm done with my node. I'm done with the left. Now I can go to the right, and I find E, which means after B, I then go to the right, I print E. There's nothing on the left and right of E, so it's done. Then I'm done with node, left is done, now I go to the right. When I go to the right, I find node C, and again, you start with the node, you start with C, then you go to the left, then you go to the right. When you go to F, it's node, left, right, it means you start with F, then you go to the left, H, then you go to the right, and there's nothing there. All right, so that's how you do pre-order. Okay, so if we repeat pre-order again, I'm simply saying here, you start with the node, then left, but when you go to the left, there's B, start with the node, then left, you go to D, start with the node, then left, there's nothing there, then, so it was node, left, we went there, then right. Now we can go to B, we did the node, we went to the left, now we go to the right. We go back to A, we did the node, we did the left, now we go to the right. When we get to C, it's node, left, then we go to F, which is now our right. When we get to F, it's node, left, then right. And that's how you print it. And finally, let's do a post-order traversal of this tree. So you can see it just needs a little bit of practice, but it's not really overly complicated. Now, for post order says that you start with left node, then right. So I'll start here. I'm at A. I'm doing post order. Because it's post order, you need to start with the left, which means I'm going to go to B. And because it's post order, I cannot print B before I go to the left, which means I go to D. And because it's post order, I cannot print D before I go to the left, but there's nothing on the left. So left is done. After left, you go to the right. Sorry, I made a mistake here. It's left, right, then node. Left, right, node. That's post order. Left, node, right is in order. So this in order here is where you go left, node, right. Pre-order there, you go node, left, right, just to make that clear. So we were saying you start at A, pre-order, you have to go to the left. In post-order, you have to go to the left first, you go to B, you have to go to the left first, you go to D, you have to go to the left. There's nothing on the left, which means you do right, so that now you can print G, then you can print your node. Now you can do D. Now that you're done with the left of B, before you can print B, you have to go to E. So now you print E, and then you can print the node, which is now B. And now that you're done with the left of A, you cannot visit A before you do the right, which means you go to the right, you find C. Before you do C, you have to go to the left. There's nothing on the left. Before you print C, you have to go to the right. You go to the right, you find F. Before you print F, you have to go to the left, means you find H. Now there's nothing on the left, nothing on the right, so you can print H. Now you're done with this one. You go to the right, there's nothing. Now you can print F. Now you're done with the right of C, which means now you can print C. Now that you're done with the right of A, you can now print A. So by observation, I want you to notice that post order always ends with your root node because it has to go to the left and then the right and then do the node. Pre-order always starts with the root node because it has to start with the node before going to the left and right. Then in order always starts at the leftmost node, right? And it always ends, we cannot say relate the rightmost node if it's there. Yeah, rightmost node if it's there. But that's in order. But the two that are easy to pick up is pre-order because it starts with the root node, and post-order because it ends with the root node. And that's how you traverse trees using in order, pre-order, and post-order. So you just need to practice this algorithm until you get it. Now, from binary trees, we talk about binary search trees. And binary search trees are created in such a way that it's easier to search for elements. You can think of binary search trees the same way we talk about sequential search versus binary search algorithms. Because when your items are sorted, it makes it easier to find your elements or to find your items, right? Because let's say you are looking for 50 in this node. In a binary search tree, the rule is that for every node, all nodes on the left must be less than the node, and all nodes on the right must be greater than the node. So you can see you have 60 here, which means all these nodes are less than 60, and all these ones are greater than 60. And this is the case for every single node in this tree. So for 50, these are all less, these are all greater. For 30, less, greater. 70, less, greater. That's how it works, which means it makes it easy for you to search for a node. And there's so many usage for these for binary search trees, which we won't really get into, but like if you think about database indexes, that's how they work. So if you're looking for 50 in this case, we don't have to visit the whole tree searching for 50. We just look at 60 and we say, is 50 less or greater than 60? Because 50 is less than 60, we can just discard the whole right tree of 60 and we go to the left and we find it, which means in one permutation or one search, you can find 50 easily. It's unlike a situation where 50 could have been anywhere, because then we have to visit every single node looking for 50. So that's how binary search trees are organized, and that's how they work. Now, with binary search trees, sometimes a common question is you're given a list of nodes, and then they say, can you draw a binary search tree such that given that these nodes are being inserted into this tree in this order? So as you insert these nodes, you have to maintain the rule that all nodes on the left side of every node must be less, and all nodes on the right side of that node must be greater. So if I'm inserting nodes into a binary search tree, and this is the order I'm inserting them with, I'm going to start with 60, which means 60 becomes my root node. So 60 goes there, and it's done. Now I want to put 50. Because 50 is less than 60 50 goes on the left side of 60. I want to put 70. 70 is greater than 60, so 70 goes on the right of 60. I want to put 30. 30 is on the left of 60 because it's less, and also on the left of 50 because it's less than 50, which means 30 goes on the left of 50. Now I want to put 53. It's less than 60, greater than 50, so it goes there. So 53 goes there. 80 is greater than 60, greater than 70, so 80 goes on the right of 70. 35, less than 60, less than 50, but greater than 30, which means it goes there. That's how you do it. It's very simple. Now we need to put 57. It's less than 60, greater than 50, greater than 53, which means it goes there. So 57 goes here. Then we go to 75. Less than 60, oh, sorry, greater than 60, greater than 70, less than 80, which means it goes on the left of 80. Next up is 32, which is less than 60, less than 50, greater than 30, but less than 35, which means 32 goes there. 40, less than 60, less than 50, greater than 30, greater than 35, which means it goes there. You see there what I'm doing there? So it can, because it's less than 60, it has to go here. Because it's less than 50, it has to go this side. Because it's greater than 30, it has to go this side. Because it's greater than 35, it has to go this side. Because for every single node, all nodes on the left must be less and all nodes on the right must be greater. So that's how we insert our 40 there. Now 77, it's greater than 60, greater than 70, less than 80, greater than 75, which means it goes on the right of 75. 48. 48 is less than 60, less than 50, greater than 30, greater than 35, greater than 40, which means it goes on the right side of 40. And then we have 45, which is less than 60, less than 50, greater than 35, greater than 30, greater than 35, greater than 40, but less than 48, which means it goes there. So this would be my tree, which means there is nothing here. There is obviously nothing here, nothing there. If I want to put these ones, nothing there, nothing there. And these are obviously my leaf nodes. If you are required to draw them, these would be my leaf nodes because there's nothing there. This is a leaf node. This is a leaf node. There's nothing on that side. And these are all your leaf nodes. So this is basically how you would end up with a binary search tree. And if you look at these nodes, you can see that for every single node that you see here, for each node, all the items on the right are greater, all the items on the left are less, which means if you go on the left of 50, you never see a node here that is greater than 50. And same applies to every single node. All these nodes on the left of 60 are less than 60, and all these nodes on the right are greater than 60. So that's how you insert nodes into a binary search tree. It's, again, a matter of practice. The other important thing you should also be able to do is to delete nodes from a binary search tree, because when deleting nodes from a binary search tree, we should not break the rule that all nodes on the left must be less and all nodes on the right must be greater, which means you cannot just go and delete a node because we have to maintain that state. So whenever deleting a node from a binary search tree, there are 4 cases you have to worry about. The first case is that it's a leaf node, like 45. It has no left or right subtrees. Case number 2, it only has a the right subtree, but no left subtree, like 40. So this one doesn't have a left subtree, it only has a right subtree. Case 3, it means it only has a left subtree, but no right subtree, like 80. And case 4 means it has both left and the right subtree, like 60 or like 50, yeah, both. So in deleting nodes, you have to deal with these 4 cases, because what you need to do depends on the case that you're dealing with. And the easiest, obviously, being case number 1, which means if you're deleting in this node, 45. All you need to do in this case, and listen carefully, is you need to set this one here to a null value, like this, to terminate it, and then you can simply delete this node. And after doing that, you can see that we have terminated there, and our 45 is gone. That is the easiest case to deal with. The next case that you deal with, case number 2, is where you only have a right subtree. Like in this case, if we try and delete node 30, it doesn't have a left subtree, it's only the right subtree. So in order to delete this node 30 here, you need to take the link of its parent and link it to its right tree. And then you can delete this one, which means after doing this, you can see that your 50 is pointing at 35 and everything else stays the same. So with case 2, where you have only a right subtree, it means you just have to take the link of the parent and point it to your right subtree, or to the right subtree of the node that you want to delete, and it's gone. So that's fairly easy. With case 3, where you only have a left tree, like deleting 80 here, it's more or less the same as case 2. You simply take the link of the parent and you link it to your left subtree. And that way you can then delete your node. And after that, you can see it looks like that. Okay. Now the most tricky one is case 4, where you want to delete a node that has both a left subtree and a right subtree. So whenever you're trying to delete a node which is under case 4, the first thing you need to do is reduce it to either reduce to case 3 or case 4. Case 2 or case 3, sorry. So you need to reduce it to case 2 or case 3 so that you can then apply case 2 or case 3. For example, let's say we want to delete node 50 and we say, let's reduce this to case 3, right? And case 3 says you only have left node, right? Only left subtree, sorry, subtree, which is what we've just done here. So let's say we want to reduce it to case number 3, and we are saying in case 3, you only have the left subtree. So how can we reduce 50, this node 50 here, so that it can become like case 3? To do that, what you do is very simple. Step number 1, go to the left node of your, or to the left subtree of the node that you want to delete, right? In other words, I'm saying, go to the left side of 50, right? Then, once you go to the left subtree, find the rightmost node from your left subtree. So I go to 30, then I find the rightmost node. So in other words, from the node you want to delete, go left. Once you go left, find the rightmost node. In this case, that node is going to become 48. This is the rightmost node. Right? Step number 3, swap the node you want to delete with your rightmost node. So after swapping, it means this node is going to become 48. This one is going to become 50. And now it's case 3, because remember, we want to delete 50 from this list. So we simply swap the values. We don't really swap the actual nodes, just swap the values. And once we do that, it means our 50 is now here, and you can see now it only has a left subtree. And once it's reduced to case 3, we can now apply case 3, which says just take the parent and link it to your left subtree. And then now we can get rid of our 50, which means eventually our tree then looks like this. So we've got our 48 here, and our 50 is gone. We've got our 45 here, because we linked 40 straight to 45. So you can see 40 goes straight to 45. That is how you deal with deleting a node in a binary search tree. So this requires a bit of practice. Case 1, 2, and 3 are very easy. Case 4 is where you need to be careful if you need to reduce your node to case 2 or case 3. So if we go with case 3, for instance, go left, find the rightmost node, or if you want to go to case 2, go right, find the leftmost node, swap, and then apply case 2. Or in this case, if we are doing case 3, we are simply saying go left, find the rightmost node, swap that with 50, then apply case 2, case 3, I mean, and that's it. That is how you delete a node in a binary search tree. And if you do it that way, you can see that you maintain the rules of your binary search tree. Okay, so that is one thing you also have to practice in case you get questions on deletions. And that's it on binary trees. Let's look at a few questions on binary trees. We have two types of questions on binary trees. The first type of questions is what we're going to look at next, where we just apply our traversals, we draw trees, and we put nodes in binary search trees. There's no programming involved. The second type of questions you get on trees is programming questions, where you have to search for nodes, find the largest number, the smallest number, and a couple of other types of questions. But you solve those questions using code. That you actually have to program those questions, and those I normally leave for last. So my advice is do the normal questions where there's no programming involved, get those right, finish all the other topics in this course, and make sure that you're comfortable before you start worrying about writing code for binary search trees, because it can take a significant amount of time to understand how to write code for binary search trees in terms of the recursion and all of the stuff that happens there. And you don't always get those questions. I mean, they are not very common. They are. I've seen them in a couple of exam papers. So normally, my recommendation is don't, always finish with programming binary trees after you're done with every single topic in this course, because that's how you maximize your chance of nailing the exam and getting a distinction. Otherwise, let's meet in the next video where we talk about some exam type questions on binary trees and binary search trees. Cheers.